In this video, we're going to talk about conic sections in polar coordinates. We're going to identify a conic in polar form. We're going to graph the polar equations of conics. And we're going to define conics in terms of the focus and directrix. Now, when we are looking at conics in our rectangular coordinates, we're really concerned about the center of the conic and the transverse axes and how far everything is on the transverse or the major and minor axes, or everything's centered, or vertices if it's a problem. We're now going to look at conics by looking at the distance between a fixed point and then to a line. That fixed point is the focus, and that line we're going to look at is the directrix. Now, with conics up to this point, we've said the conic that has a directrix was a parabola. But what if I were to tell you that all conics have a directrix if it's in polar form? We talked a little bit about eccentricity in a previous video. Now we're going to talk about eccentricity a little bit more. We have this fixed point here, which is our focus. We have this fixed line, which is the directrix. And then the eccentricity will be the ratio from this focus here, this point, this focus here, to this point P. This is a point that's on the graph. And from this point P to the directrix. Now, this line, this distance from this fixed point P to the directrix will always be perpendicular to the directrix. And that's how we're going to define eccentricity. Well, we kind of defined it before, but we're kind of looking at it a little bit more. So how did we get to this point? Well, we have this point O, which is the origin if we're in the XY plane, and in the polar plane it is our pole. We have some sort of rotation here, which is our theta, and then we have this distance r. So now we have this point in polar of our theta. Now the distance traveled between this point and the y-axis if we're in the xy plane, or theta is equal to pi over 2 in the polar axis, we know that's x if we're in the xy plane. And so that means that if this distance is x, that means x can be replaced with r cosine theta. Now we also know that the distance from the line theta is equal to pi over 2 to this directrix, we're going to call this the distance d. So using this ratio from the point P to F, which is our focus, and then point P to the directrix, is going to be r, because this is my distance r, and then it's going to be d plus r cosine theta, d plus r cosine theta. If we solve for r now, we're going to get this equation. We're going to get r is equal to ed, 1 minus e cosine theta. Now, if my point that I'm looking at is on the other side, on the left side of theta is equal to pi over 2, then of course what that does is change this sign here to a positive. So we know for an conic with a focus at the origin, so if it's a conic that has two foci, then one of them has to be the origin. The directrix will be the line x equals plus and minus p, where p is a positive real number and the eccentricity is a positive real number e. The conic will have a polar equation in this form. So in other words, my conic is going to be opening left and right if it's a parabola, if it's in this form, because it'll be, the directrix will be x equals, so it'll be opening left and right. And if it is opening up and down, if it's a parabola, it will be sine. Now we know from 10.1 that if my a value was bigger than c, we're in an ellipse, that means my eccentricity, that ratio, must be between 0 and 1. Now this a and c bit's coming from how we define the ellipse. c being the distance from the center of the ellipse to the foci, a being the distance traveled on the major axes from the center to the vertice. And that gives us the fact that if we have an ellipse in this form, I can tell you it's an ellipse based on the fact the ratio is less than 1. Now, in 10.2, we talked about hyperbolas. And in hyperbolas, c being the distance from the center to the foci is obviously larger than the distance from the center to the vertex of one of the parabolic shapes in the hyperbola. That'd be the distance a. That means that ratio has to be, e is the ratio, has to be greater than 1. And lastly, when e equals 1, the conic is a parabola. Sine is used, then the directrix is above or below the pole. If cosine is used, the directrix is left or right of the pole. And remember, a focus, if you have more than one, is always located at the pole. Now notice the equations up here. Let's talk a little bit about the equations. The important piece is this being 1. Once we have it so that there is 1 in this position in the denominator, I can easily figure out what E is. Once I figure out E is, I can figure out what P is and everything else. So we ask ourselves, is it in the right form? Well, A is, but B is not. So if A is already in the right form, then I'm going to first determine what kind of conic I have. The equation, of course, again, generically, is R is equal to EP 1 over, and I'm going to use a minus because I have a minus here, E, the cosine of theta. So this coefficient E happens to be 1. So that because it's E, we know this is a parabola. Now this is important. Since this is a parabola, then we know the distance from the vertex, only for parabolas. The distance from the vertex to the focus is the same distance from the vertex to the directrix. This only works for parabolas. Just want to say that. Okay, so now let's go ahead and figure out. We know that the focus is, or the focus is right there. So I'm just going to zoom in so we can have a better view of this. This is where the focus is. Now, we know that the numerator 2 is equal to EP. We happen to know that E is 1, so 2 must be where P is. If you're not certain whether it's left or right, because remember this is cosine, so my directrix will either be x is equal to 2, or it's going to be x is equal to negative 2. What we can do, since this will open left or right, let's put in 0, or let's put in pi and see where we end up with. So I'm going to put in theta is equal to 0. When I get theta is equal to 0, I'm going to get r is equal to 2 over 1 minus 1. Well, this is undefined. So that means that I'm going to probably be opening to the right. So let's try theta being pi. So r is going to be equal to 2 over 1 minus a negative 1. So r is going to be 2 over 2, or in other words, 1. So I go out, I'm going to call this 1 to make it easier. I'm going to call this 1. I'm going to go out 1 on the angle of rotation of being pi. So right here is my vertex. That means, so this is negative 1. I'm going to go over here. This will be negative 2. So I know my directrix is going to be right here. X is equal to negative 2. Now I know I'm going to be opening in this direction, right? But I don't know exactly how wide this is. So to figure out how wide it is, I need to put in theta is equal to pi over 2. So when I put in theta is equal to pi over 2, r is just going to be 2 over 1. So I'm going to go out 2, 1, 2, and there's that. And of course, we should have had a polar graph here, but that's where it'd be. When theta is equal to 3 pi over 2, my r is also 2. So 3 pi over 2 is straight down, and I go out. Again, I need to make sure I scale this 1, 2. So this is the point on the polar axes. This would be the point 3 pi over 2, comma 2. Let me scale this right. And this would be the point pi over 2, comma 2. So I know that this is my parabolic shape. I also know where my vertex is. I know the focal diameter. The focal diameter is this distance. And I can clearly count and see that that focal diameter happens to be 2. Now my second example here is not in the right form. That's because right here in the denominator, that should be a 1 and I don't have that. So I'm going to divide every term in my fraction by 2, in other words, multiply by 1/2. And I get r is equal to 3 over 2. 1 plus 1/2 the sine of theta. Now I happen to know that right here is where my focus is. I also know that this number in front is my e. E is the coefficient on sine is my e, so e is equal to 1/2. That tells me since e is less than 1, we have an ellipse. So I have this in ellipse. And I have sine, so I don't know if my ellipse is going to be orientated this way. So let me erase that because I don't know if it's orientated that way. I don't know if it's orientated this way. But I do know that the major axis is going to be, if we were in, again, if I should have a polar graph here, it would be theta is equal to pi over 2. So my major axis is going to be on the line theta is equal to pi over 2. Now, I know what my p is going to be because 3/2 is equal to EP. So 3/2 is equal to E is 1/2 times P. So multiplying both sides by 2, I get 3 is equal to P. So then do I have Y is equal to 3 or do I have Y is equal to -3? If I'm not certain, and I'm not going to memorize any of that, I'm going to start putting in angles. So I'm going to put in theta is equal to pi over 2. So I put in theta is equal to pi over 2 back into the original one. And I get r is equal to 3 over 3, the sine, I got the 3. The sine, so 3 over 2 plus, the sine of pi over 2 is 1. So we get 3 over 3, which is 1. Now, oh, actually, you know what? I'm going to scale this out again because it's really hard with this to see how it's scaled. So that's 1. And now I'm going to look and say, okay, well, what happens when theta is 3 pi over 2? Well, when theta is 3 pi over 2, I'm going to get 3 over r. Let me do this. R is equal to 3 over 2 minus 1 because the sine of 3 pi over 2 is -1. So r is equal to 3. So 1, 2, 3. In polar form, this is 3 rings out, pi over 2 pi over 3 pi over 2. 3 pi over 2. So it's going to be orientated in this direction. That means my directrix must be the line y equals 3. So here's 1, 1, 2, and 3. So here's where my directrix is. Y is equal to 3. Now I'm going to take this off and I'm going to get better points. So I'm going to use the point theta is equal to 0. So r would be 3 over, the sine of theta being 0 is 0. So that's 3 over 2. So I'm going to go out 1.5. So I'm going to go 1.5. So here's 1 and here's 2. So here's 1.5. When theta is equal to pi, r is going to be the same thing, 3 over 2. So I'm going to go out pi. Here's 1. Here's 2. So here's 1.5. So here is a better shape. It's kind of almost circular. Actually, that's a Taylor shape. In your mind and in my mind, that is a beautiful ellipse. Reality is that is awful. It's kind of a squashed egg shape, but it's a beautiful ellipse. Okay, the focal diameter you can see is going to go from side to side. So this is my focal diameter. I also know that this distance from the focus to the vertex has to be the same distance down here. So here's where my other focus is. So if that distance from the focus to the vertex is 1, then from my other vertex, I also have to come in a distance of 1. Let's take a look at my last example here. So again, we know that E has to be 3. We know that 4 has to be E multiplied by P. So 4 must be 3 multiplied by P. So I have 4 over 3 is equal to P. My E being 3, we know this is hyperbola. So we know this is a hyperbola. And because it's cosine, we know that my P value is either x is equal to, so I'm opening left and right, so I either have x is equal to 4/3, or I have x is equal to negative 4/3. Now remember, I don't take the time to memorize this. So let's start taking some points. So when theta is equal to 0, I'm going to have r is equal to 4 over 1 plus 3. So r is going to be equal to 1, because it'll be 4 over 4. So here is 1, so right here. And here's where my focus is. If that's where my focus is, and I'm opening left and right, my directrix must be at 1 1/3. Positive x is equal to 1 1/3. So here's where my directrix is. X is equal to 4/3, or in other words, positive 1 1/3. Now, let's go ahead and find another point. So we have theta is equal to pi over 2. When theta is equal to pi over 2, we're going to get r is equal to 4. And the same thing when theta is equal to 3 pi over 2, because we're working cosine. So pi over 2, I'm going to go 4. 1, 2, 3, 4. 1, 2, 3, 4. And so I have this hyperbola. This is half of the hyperbola is going to be opening in this direction. Now, I know that if I put in theta is equal to pi, I should get my other vertex. So I put in theta is equal to pi. I'm going to get 4. R is equal to 4 over 1 minus 3, because the cosine of pi is a negative 1. So I get 4 over negative 2. So I get negative 2. Now, again, this would be better if I had a polar graph. Here is pi. The fact that it is a negative means that the negative radius, that means I'm going to reflect over my pole, and I'm going to go back 2. So I'm going to reflect over my pole. So I'm going to reflect over my pole, and I'm going to go 1, 2. So here's where my other vertex is. My other vertex is going to be, in polar form, it's going to be pi, comma, negative 2. And in rectangular, you can see it's 2, comma, 0. Now this is my focal diameter right here. That means for my other part of my parabola, that I would go a distance of 1 from the vertex to my other focus. So here's where my other focus is. Along where the focus is, I'm also going to have this mirror image. So here's my other side of my hyperbola. So I found my focus, I found my vertices, and I could find my center if I was so inclined. If I'm asked to find the polar equation with this given information, I know if E is less than 1, then we have an ellipse. So we know this is an ellipse. We also know that this one is an ellipse. And we know that this one is an ellipse. I must have really liked ellipses this time. You never know. Okay, so we know that we have an ellipse. We know the focus is at the origin. And we're given this directrix. Now, We know from doing our graphing exercises up above that if x is equal to 4, this is my p-value is equal to 4, and since it's on the right side of my focus, not on the left side, I must have r is equal to, it's going to be my p-value multiplied by my e value over 1, and it's cosine. And because my directrix value is positive, I know I must have a plus the cosine. Oh, don't forget my e. I got so excited. I was excited with my cosine. It would be 1/5 the cosine of theta. If we look at our next one, we know it's an ellipse. We know our e, so we know we have r is equal to, our y is always going to be, or our p is always going to be 2. So 2, or positive, excuse me, 2, it's not always 2, it's positive. So 2 over 1/2, because that's my EP. And then I have 1. Because y is negative, we know it's going to be y is equal to a negative number. Because y is equal to a negative number, we know in the denominator it's going to be 1 minus. And in particular, because it is y equals, we know this is going to be sine, so it's going to be 1 minus 1/2 the sine of theta. And similarly, we know this is going to be r is equal to 5, because it's always positive, and the p in the numerator in this form is always positive. And then it's going to be 3/4, 1. Because this is y is equal to a negative number, it's going to be y minus, and then my e, which is 3/4. And then because it is y equals, we know this is the sine of theta. And that's it.